Hello, David.
Hi, Sigmund. How are you?
I'm good. How are you?
Pretty good.
Nice.
Maybe give a minute to everybody else,
Yeah, sure.
whoever is interested in joining, to join, and then we'll get going.
Mm. Okay.
Okay, let's get going. Um, where Sigmund, why don't we start with your update? And while I pull up my design update, it's going to take me a couple of minutes. So
Yeah.
why don't we start with your routing and analysis?
Yeah, of course. Yeah. So let me share my screen first. Do you see my screen?
Yes.
Yeah. Okay. So last time I worked on CPU to CPU UCIe connection and um, signature dissimulation. And so as you already know, I move on to the HBM to CPU routing. So, uh, so
Right.
yeah. So I connected one row of the CPU to HBM connection, and it looks like this now.
Yeah.
So I first have to say the routing topology for Boon. Mm. Yeah, so for CPU to HBM, I used this routing topology. So I put the VDD on the top and alternate the signal, ground, and signal, and stagger the signal a little bit, and repeat the pattern, ground, signal, ground, stuff like this. Um, yeah, so this is how it looks like. So these are signals, and these are planes. So I mean
Okay.
the ground, yeah,
Yeah.
between the
Right.
signals, yeah. So I added all the grounds between the signals, and uh, the simulation is still running.
Oh, it's
Yeah,
still running? Okay.
actually,
Uh,
I run the simulation last night before I sleep, but it pops up an error message. I miss the adding the so I fixed the VSS net in the
okay.
layout. Yeah, so I just started the simulation, so it's still running. Yeah,
Okay. Yeah. It will come. So you're running the long one, right?
yeah. Actually, I run so to see the crosstalk as well. I added main ports here, um, 96. So So there's 48 signals in one row. So I just added all the signals
Oh,
in.
okay.
Yeah.
No,
So
because
yeah.
okay, okay, yeah. Then so uh, okay, so just a little bit of background for everybody else. So the way we set this up is we didn't know any better at the time, and the way we did it is the front row of front basically when you look at the HBM memory bumps and the HBM5 bumps on the other side, basically we're connecting front to front and back to back, right? This is to see what will actually work, what will not, right? This will that so we by doing these connections, what we end up is front to front is going to be the minimum length connection, and back to back is going to be the maximum length connection. That's going to give us a boundary how the signal integrity looks like, kind of worst case and best case. And if the very long routes, which are back to back, don't work, we may have to flip the HBM5 on the CPU side, such that we connect front to back and back to front, right? But we'll see how the signal integrity for this looks like, and crosstalk and things like that. Yeah. So
So are we using the HBM IBIS model for the SI?
we don't have IBIS model for SI,
Well,
but we have.
we do have an IBIS model for HBM too, so we could use that and just hack it.
Oh, okay. That's that in that package that which you sent me.
Yeah.
So for HBM4, so the way we set up simulation is I give to Siemens some parameters in terms of voltage swing, ramp times, driver impedances, path capacitances, and so on. I think that is going to be good enough for first view whether how the channels look, right?
For the channel, yeah.
Right. Because we don't have the channel yet, really. So let's get that first, and then we'll switch to HBM2 PHY and see how that looks, right? Because I mean to the HBM2 IBIS model. Once we kind
So
of
when you said you don't have a channel, you're saying you haven't routed this channel that you're showing right now.
we just routed it, and Singman is doing the extraction.
Okay. All right. So is John, is he working with John on this, John Chaka? Or Mohammed, they can help.
I'm keep I keep talking with John about the SI simulation. Yeah.
Okay, good.
Yeah.
Yep. Okay. Great. Yeah. So we will know. Tony, I think you missed a couple of meetings on the UCA side.
Yeah.
On the UCA side, we are done. We are passing the 32 gigabits on a by 32 with flying colors.
When you say passing, you're talking about functional simulation or SI or both?
SI.
Okay, awesome.
Yeah.
Yeah. This is the I CPU to CPU UCI connection.
Yeah.
And you obviously don't have an IBIS model for that, right?
Yeah, I didn't use the IBIS model. Yeah. I just see the channel. Yeah.
I don't have anything for that.
Yeah, but I just applied
Are you using the compliance testing, or you just ran the straight SI?
The straight exit. Yeah.
Okay.
Yeah.
Good.
Yeah.
Okay, good. Yeah, so we'll know on Monday then how this looks, Singmin, and when we talk, we can decide how do we approach this.
Mm, yeah. Yeah. Sounds good.
Okay. Yeah. Okay. So then let's switch to my update. So what I did was, the right window. No, no, not this one. Sorry. Okay. Okay, this one. Um, Okay, yeah, this one. So, in order to make this a little bit more realistic, what I created is IO chiplet that basically has UCE on one side and PCE on the other. Fairly straightforward uh,
Wait,
design.
zoom out again. You said UCIe on one side, PCIe on the other?
Basically, so these two and these two are the IO chiplets. And each IO chiplet will have basically UCIe on one side to connect to the CPU and PCIe on the other side to connect to the outside world. I kind of eyeballed the bandwidths and somewhat for visual purposes, kind of try to match the number of PCIes to the number of UCEs, and such that the bandwidth is also matched on both sides. So that should give us matching bandwidth. So that's my minor update. So kind of going on in parallel with what Signin is doing.
Now, are you using the SI, I forget what you call it, the new standards that we have for
Sorry, say that again.
integrity? Yeah.
Say that again.
I said, are you using the new I forget what you call it, the signal integrity specs that we're using for defining these specs? Or you just
Sorry, I don't understand what do you mean?
the CDX SI format?
Not yet.
Okay.
This is kind of this is going on in parallel,
Okay.
right?
All right.
Like,
So,
kind
so
of trying.
you're just doing it using the traditional stuff.
Yes, it's just the traditional stuff. The intent is really to get the definition hashed out with this design as well, right?
Okay, so it's actually, it's good. We have a test case, and when we start pipe cleaning, we have the test case rather than doing it the other way around, building something and then building a test case.
Exactly.
Yeah. Okay.
Yeah. On the power side, Tony, I think you missed that. So we talked about how to handle power. And one thing that seems to be interesting these days is putting the regulators on the package.
Yep.
So the way this is set up is there is 48 volt coming in that gets down converted to 12, then 12 to 5 goes into the package, and then there's a whole bunch of regulators here which then convert to the corresponding supply, right? Whether it's the HBMs, UCEs, core, and so on.
So 12, this is 5 volt, you're saying?
In the package, we get 5 volts in.
Okay. Is that the only voltage, or you have other regulators for?
That's going to be well, we set up 1 voltage to come in. If any other voltage is needed, that gets converted on the package.
Okay, so the 5 volts is into the package, and then then you're putting VRMs inside the package to do generate all the others.
Correct.
Cool.
Yeah, we have not. I have not looked at sizing the regulators yet. In terms of to see whether one, two, like one per chiplet or two per chiplet, right?
Right.
Depending on the regulator capacity.
Yeah.
But
Do you have real,
we'll get to that.
what is this Dunka chiplet?
That's my tool.
What tool is it?
That's my tool.
Okay, so this is not Power Meter, it's a new name or it's a new tool
It's a new name.
for Power Meter?
Yeah, because
Okay,
it got a little bit more than power stuff in it.
okay,
Yeah.
very
But
cool.
yeah, right. But looking at the power stuff, that's how it's set up right now. And I have the values for all the powers. I guess right now we're looking at, what is it, 600 watts total power, including all the regulators and everything.
Right. Now, do you have real
Right.
models for any of these regulators?
No, at least at this stage,
Okay.
I made a guess about the efficiency of the regulator,
Right.
such that I can account for power loss inside the regulator. So we are at 592 watts.
Okay. And do you have like a dummy chiplet for the regulator?
Not yet. Right now, it's just a module. How do I say, a virtual module? I don't have the physicals of it yet, but
Okay.
we'll get there. We'll get
Okay.
there.
So you are planning on doing that.
Oh yeah.
And this will be on the interposer, so it's not stacked or anything, or is it stacked?
It's going to be on the bottom of the interposer.
Bottom of the interposer. Cool.
Yeah, we are gonna put it on the under the chiplets or under the places where it's needed and see how that looks.
Cool.
Yeah, we'll see how it looks. And at that time, we'll kind of define the power planes and be able to look at
So
power integrity.
so is it, I mean, are the regulators actually so how do you mount that on the substrate? Or are we even doing a substrate?
We'll just it will be mounted on the other side. How do we really want to get into whether that's physically possible, how difficult it is for manufacturing, or just kind of assumed, okay, somehow these will appear on the bottom side and everybody's happy?
It might be nice, but I mean, for demonstration purposes, yeah. I mean, it's
Yeah.
I mean, it's not really, that's not the way it would really be done, right?
Yeah.
I mean, the other alternative is you could embed them in the substrate
Yeah.
because that's the way, you know, AMD and Intel do it.
Yeah. I don't know how much of that is public information, how exactly it's done.
Well, no, I mean, it's their specific rules are proprietary, but I mean, they're fundamental concepts, right? You just embed in the substrate.
Yeah.
And well, you can embed it in glass too.
Yeah.
But
I'll tell you what, let's put it somewhere and let's get to the point where we are in a position to talk about
yeah,
embedding.
so you're just working on the analysis side of it, but
Yeah.
because yeah, Sigmund, I'm sure the stuff that you didn't support double-sided and embedded structures, but there is Upsolix is working on that glass interposer. They're working with the Georgia Tech. So, and we could check to see if we can do some stuff generically for demo. You know what I'm talking about, right, Sigmund?
Sorry, I miss
So,
sorry.
yeah, I don't know how involved you are involved with the NAPMP program.
Yeah, I'm working
So,
with Dr. Key, yeah.
that technology does support the glass interposer technology supports embedding
Yeah,
components.
yeah, yeah.
So, you might want to talk to your professor to see if we can do like a dummy tech file that would allow us to do
Mm.
this. You know,
Yeah,
without
yeah.
using any real rules. We could just, obfuscate the rules and I think he would,
Mm.
and you can come up with some of the different structures.
Yeah, definitely.
But,
Yeah. Yeah.
yeah.
Actually, yeah, I'm gonna tell about our project and I'm gonna like suggest like collaboration
Yeah.
uh for the OCP project
Yeah.
next week.
Yeah,
Yeah,
we
Yeah.
can
Tony.
set up a call. We have to be careful. I mean, it is a government project, so we have to be very careful. We can't just, arbitrarily
Mm,
just copy stuff. But
mm,
yeah, I think if
So,
we come up with a dummy tech file there's nothing secret about embedding structures and
yeah.
substrates. So
Yeah.
but if
mm.
we could
Yeah.
have
But
a
so,
dumbed
so
down, simplified
Yeah.
technology, that would be
yeah.
Okay. Yeah, yeah. I got your point. Yeah.
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 Mm,
Tony, one thing I have been I mentioned to Sigmund is I think it's going to be a good idea, and it's going to work for everybody pretty well. Apart from NAPMP, as make sure that that the work that Sigmund is doing here is useful for his research as well, right? Because anyway,
Absolutely.
read that research
Yeah.
chiplets. It's everybody's seeing the same problem. So
Yep.
maybe there's going to be a way to collaborate, kind of at OCP level with Georgia Tech and and
Mhm.
NAPMP and everybody, and see what solutions come out of this, especially what research comes out of this.
Right, 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 right. So I'd like to get Mohammed involved in this too. So I know you're working with
mm,
John, but I don't think John's supporting existing tools and methodology. This is kind of new stuff that we're looking into. So
mm.
Mohammed can help in that. So I'll talk to him first,
Okay.
but we
Yeah.
can start thinking
Yeah.
about how we're doing this. Now, are you using UPF in your docket tool to define this whole power network?
UPF.
Uh,
Yeah.
UPF is going to be output of this and input to Sigmund. But
Okay. Okay.
we are not there yet, right? We have
Mm,
only a kind of like a virtual idea for what power is going to look like. We kind
Right.
of we
mm,
we we actually we got that idea very recently, so we are not there yet,
mm,
but
yeah.
we'll get there.
Yeah, that's fine. But I definitely like this. I think
Mm,
I've been out of pocket for several weeks, but it
Yeah.
looks like you guys have been busy. So
Yeah.
good stuff.
Yeah.
Yeah. Please let me know if you need any help on my side to contact with Dr. Bakir.
So David, I know this is all cool stuff, but
Yeah.
again, we just increased the complexity probably by 2x. So do we want to kind of keep it simple for now and then build that on for future stuff, or do we want to just go for broke all in one shot?
Um.
Something to think about.
So probably the way I think to handle this is we'll just be chipping at different problems as we go along.
Mhm.
I agree the complexity gets a little bit bigger, but it's always like that, right? And see how that works. Then there is the POC workstream that's kind of looking for direction a little bit. So we may collaborate with the POC workstream in some way or fashion. What that
What is
means,
POC Workstream?
proof of concept, right? That is
Is there a
trying to,
Workstream for, there's a Workstream
yes,
for POC?
yes,
Really?
they are. Some of the issues we are seeing in terms of, okay, how do I connect these and how do I place these and how do I design this? I think we are a little bit on the forefront of things, right? Because we are
Mhm.
talking about compatibility and packaging and models. The others are slowly warming up to this problem. I know this morning in the OC meeting, the question was, right, how do right, people who think about their chiplets in terms of RTL, they don't know how to connect to anything else yet, right? What does it mean to have a package model and bump map, and how do I create that, and how do I make sure it's compatible? POC is looking at the really practical stuff of simulating and integrating, at least functionally integrating chiplets from different vendors. And the
Mhm.
system workstream is looking at that too. So we are a little bit ahead, I think.
Mhm.
Right. So I'm not, it's a complex problem. And the only way to do that is just keep chipping at it, and at some point we'll have a solution.
Mhm. Okay. The just sounds good. The so the PCIe interface, is that gonna go out through the bottom of the interposer?
Yes.
Yes.
Space.
Yeah.
So okay. So you'll have UCIe and HBM is on the top side, die to die, and then everything for the bottom side will go through TSVs for your PCIe, power and ground. You'll put
Yeah.
RIMs on the bottom,
Yep.
and okay. But it's possible we may just have I think the way the Solix is doing those VRMs would be embedded right in the middle, below the chiplets, and you can do kind of all your power planes right in there.
Yeah.
In fact, support power planes embedded within the glass interposer, which is kind of cool.
Yeah.
So
Yeah.
rather than having to bring everything through TSVs, you just go straight down to the power planes. But again, how proprietary that is, we have to hack something up that makes reasonable sense for
Yeah. I got,
somewhat realistic technology, but without, giving away anybody's secret sauce.
yeah, it doesn't have to be. I mean, there is nothing. Right. People have been embedding in the core forever.
Yeah.
Right. So we'll just assume a cavity and put it in there. Right. It could be as
Well, yeah,
simple as that.
you could just embed it in the substrate, right?
In the builder players.
Hmm?
You mean in the builder players, or in the where in the substrate?
Just in the substrate itself, right? Rather than embedding it in the glass interposer. Just you're always going to have the
Oh, okay.
yeah.
Yeah.
So you
I
could
I I
just
I see. I see. Okay. So
yeah.
yeah. So we haven't really talked about that, right?
Right.
The way we are designing this right now, basically we are looking at the glass interposer.
Mhm.
We haven't really focused on what's going to be below that.
Right. So
Um,
yeah, so that you know, there's a couple routes we can go, but you know, the physical implementation, we should
yeah,
need
I
to come
think,
up with that strategy at some point. Have we implemented the interposer yet? The layout?
yeah. So Sigmund was just showing some of the routes when we started. Remember,
Okay, so
that's the interposer layout.
okay, so that's top side. Are there TSVs in there, or is it just the top side routing?
Not yet. Right now we don't have anything that goes through yet, right? I just added those IO chiplets. We will have something.
Okay, cool.
Yeah. I think putting the VRM on the bottom of the interposer for now is going to be fairly representative of, or similar to putting the VRM in the substrate below, right? It's
Yes.
about the same
Yes.
thing, right?
Yeah.
So
Yeah.
yeah, the idea is to show that any benefit of current reduction, right? Power reduction, we'll be able to
Yep.
see some thermal issues. Probably, especially, would be very interesting to see the inductance reduction on the power plane and how power integrity looks, right?
Exactly. I think you're going to see better power integrity. So
Yes.
to that point, if we did, you know, one demo where we didn't have BRMs and ran power integrity, you know, versus the other, that you know, that's how we could have a, you know, here's what it is, and then you know, the next generation of this chiplet has the VRMs embedded, and you could see better integrity. That would, you know, I think at a high level demo, if people could see that would be
Yes. Yep.
a little more. Oh, I see what you're doing and why you're doing
Yeah.
it, rather
Right.
than, oh, we're doing it because it's cool, right?
Yeah.
There's real value. All right, excellent.
Okay.
Still,
So
still man
that's
45, right?
yeah.
Yep. Okay.
That's all updates from our side. Anybody else have any questions, comments? Okay, if not, I guess we'll conclude for today and we'll meet again sometime next week. In the meantime, we'll keep on chipping at this design.
Great. Thank you.
Thank
All
you.
right. Thanks everyone.
Happy
All
Friday.
right. Bye.
Yeah. Happy Friday.
Yeah.
Yeah.
So, bye.
So.
I'm done. I told him.
Hi, Tony. Tony? Hi, Tony, can you hear me?
Yes.
Hi, my computer just crashed a few seconds ago and I had to just reboot, so I was hoping to get yourself and David.
Yeah, I
I-
can't. Yeah, I can't right now. So the
all right, you wanted to,
meeting's over.
right, okay.
I might have time at
Probably only take about 4 or 5 minutes. It wouldn't even take 4 or 5 minutes.
yeah, I'm
You
literally
tell me.
walking out the door. Sorry.
Huh?
Literally walking out the door.
All right, okay. Well, I'm about to publish the documents and I just wanted to get clarification on 3 points. So
Okay.
I will go ahead with and just go ahead and do it then.
Okay.
Okay,
Which
all
document?
right. The JEP 30 part model, which includes the 3D stack. This was all approved late last night.
Okay.
I'm just putting it onto the finishing documents, but IEC throw a boner at me saying that they wanted the magnetic sensitivity to be changed to electric magnetic sensitivity, and we wanted it to be changed to voltage magnetic sensitivity to distinguish the difference between a voltage magnetic sensitivity or current magnetic sensitivity.
Okay.
We also wanted resistivity to be changed to electric resistivity to distinguish it clearly from thermal resistivity and
Yeah.
acoustic resistivity.
Yep. Yep.
And,
Okay.
and we wanted voltage temperature sensitivity to be used instead of thermoelectric sensitivity, because the thermoelectric could be related to voltage or could be related to current.
Right. Okay. Yeah, I would agree with that. Okay. All right. Thanks, Michael.
Okay, all right.